Okay, in this video we're going to take a look at how to identify the significant figures in a number. Remember, significant figures refer to the precision with which something was measured, and so the amount of significant figures that are involved in the numbers in the calculation affect the amount of significant figures or the level of precision that you can give in your answer. I found that the box and dot method is a nice, simple, three-step process for determining how many significant figures are in a number. So if we look at this first example, 123.01230, how many of those numbers are significant? Well, here's the method we'll use. First, draw a box around all non-zero digits, beginning with the left and ending to the right. Okay, and so if we're doing that in this situation, our box would look like this. Any zeros that are sandwiched between non-zero digits are included in the box. For example, this 0 right here, it gets included because it's between some non-zero digits. Step 2 then says, if a decimal point is present, draw a box around the trailing zeros. In other words, any zeros that come after the original box. So in this number, we would box that final 0. Step 3, easy, count the digits in the boxes. They are the significant figures. So in this first example, we would have 1, 2, 3, 4, 5, 6, 7, 8 significant figures. Every digit there is significant. We'll apply these same 3 steps for a few more problems so you can get the hang of this. In number 2, first we're going to draw a box around the non-zero digits. Zeros stuffed in the middle are sandwiched between non-zeros, they get boxed as well. Then, step 2, if a decimal point is present, there's not a decimal point, so we can move on to step 3 where we count the number of digits, and we would see that there are 7 significant figures in example 2. Number 3, same idea, box the non-zero digits starting with the left, going to the last non-zero digit. In this case, everything has been boxed in, so we can go right ahead and count, and we would find that there are 7 significant figures. Again, starting with the left, moving to the right, we'll box our non-zero digits. There's no decimal point, so these zeros do not get boxed in, meaning we have just 3 significant figures. Same number, it seems, in number 5, but because of this decimal point, these trailing zeros, any zero that trails the original box, is also considered significant. In other words, here they measure to the nearest hundredth, here they measure to the nearest tenth. And so in this number, 10,100, we actually have 6 significant figures. 1,000, but there's a decimal point with a 0 after it. Okay? Using our 3 steps just to make sure we've got it, we box the non-zero. Then, because there's a decimal point, we box any trailing zeros, meaning we have 1, 2, 3, 4, 5 significant figures. Compared to, if we just had the number 1,000, this 1 would be significant. Without a decimal point, none of these zeros would be significant. There would be just 1 sig fig. And number 7, this one looks a little different than what we've seen, but the same method will work. We start by boxing the non-zero digits, and then because of the decimal point, we box trailing zeros. Just a reminder that trailing zeros are the zeros which come after the original box. These do not count as trailing zeros. So we're not looking for things that trail the decimal point, we're looking for zeros that trail the original box. So we would have a total of 2 significant figures. Let's take a look at what that looks like when a number is written in scientific notation. For example, number 6. The same 3 steps will work, so we can box our non-zero digits. And then there is a decimal, but there's nothing trailing it, so we see right here that we have 4 significant figures. In number 9, 1.6 times 10 to the negative 19. We still box the non-zero digits. Because of the decimal point, we would box this 0 as well. And so we would see that there are 3 significant figures. In 10, the 3, the 5, and the 7 are our non-zero digits. Because of the decimal point, this 0 is also considered significant, and so we have 4 sig figs. Perhaps you're noticing a trend in these last 3, and that is that if something is written in proper scientific notation, every value is significant. In other words, in number 11, there are 2 sig figs, and in number 12, there are 3 sig figs. All of these are significant because there's always a decimal, and so any zeros would be significant. If it was only measured to one significant figure, this value would just be reported as 5 times 10 to the 10th, rather than 5.0 times 10 to the 10th. This idea brings up kind of the value of using scientific notation with significant figures. Sometimes it's necessary to report your answer in scientific notation simply to convey the level of significance or precision needed. Okay? So all the significant figures must appear before the times 10 to whatever power when writing in scientific notation. So our practice problem is if we have the number 500, but let's say we measured to the nearest tens. Well, then we can't just say 500. That currently only has 1 sig fig. So in order to write that with 2 significant figures, we would say 5.0, there's our 2 sig figs, but then times 10 to the 2nd power, which makes it equivalent to a value of 500. With 3 sig figs, we would simply add another 0 after the decimal. Oops, this would still be a 2. Still has to be equal to 500, but now we're showing a total of 3 significant figures. If we wanted to show 4 significant figures, we could write it as 5.000 times 10 to the 2nd, or 500.0 would also show a value of 500 with 4 significant figures.